try to build up the better way. So here I borrow, I dig out from the garage. The case is very old. Okay, and I try to demonstrate the things. So here we can see the better view is this. Let this one, the right one is IJK. Okay, this IJK right now aligned to here. And right now we want to do the transformation is this. And if you can see, if this is the coordinate system, I'm going to do a sequence of two operations. So right now I put an overlap, but here you imagine this origin of both of the origins are overlapped here. Okay, so right now this is the IJK coordinate systems aligned to here. So the first one you can see is I rotate about the z-axis by an angle theta. Okay, so I go to these directions, and now the second one is I rotate this axis by, it's not fixed, rotate about this axis and by this angle. So in this way, this one aligned to as easy. Okay, so that became the clear view of these things. So again, if you can see, right now for the IJK system, again, I first rotate about z-axis by theta and align this one to the, and then the second one is I rotate in this angle. So right now this is our S-easy coordinate systems. Okay? So right now under these situations, for the first rotations is from our IJK XYZ in IJK coordinate systems and to so this is the IJK coordinate system. Right now we're rotating into these orientations. So about the axis by theta. So this is the first coordinate systems we achieve. And under this situation, you can see basically I move to here, J move to here, K keep the same. Okay, so right now let me see. For the first coordinate system, I don't care about the coordinates, but basically the K is the same. And let me say this is 1. I forgot the symbol I used last time, so let me just use 1 and whatever. Okay, so let me use whatever the system. So let me call this 1x, 1y, and k is the same. So under this situation, because this is a theta, so you can read for the one axis we decomposing. So this is IJ coordinate system, and right now this is the axis of the one axis. Okay, this is the theta. We decompose into the two components. This is a component in I direction, that is cosine theta. This is a component in J direction, so that is sine theta. And that's the way we write up the tables here, and that's 0. And this is a y-axis. For the second one is the I y-axis. So that can be, let me call the 1 y-axis. So for this one, you can see it's project into the projections. This projection is cosine theta in J direction, so cosine theta. And then this is the sine theta amount, but projecting into negative I direction, so that's negative sine theta, 0. And k basically is the same as the original, so 0, 0. So that is what we defined as the R1 per the symbol we used last time. Okay, good? Okay. And right now, for the second operations, I think, let me, whatever, okay, so using this one. So that is for our coordinate system 1, okay? So right now, we want to transform into the coordinate system. So for the second operation, so right now, this is the first operation. The second operation is we're going to rotate about this axis by the angle. The angle is this amount. This amount is 90 degrees minus L. So we see what happens here. So right now I rotate about this axis by this amount. So in this way, you can see this aligned to that directions, aligned to that SEZ coordinate systems. Okay? From here to here. Okay, so under this situation, and you can see right now for these systems, we simply rotate about this axis and by this amount. Okay? So this is about this one. So here we can say in the new systems, so that is our original, the result of the first operations. So right now we want to rotate. Right now we want to rotate by this. Okay, so original z axes are aligned, and right now we simply rotate in this way. Okay, so in this way you can see, and right now in terms of our orientation, you can see this axis in our symbol is IX, right? So IX after this rotation, IX aligned to which axis? Aligned to S, right? If you have any questions, you let me know. If you don't have any questions, let me know. Okay, keep a face, keep the emotional face. Okay. Okay. So in this case, the IX actually is going to align to S. So that is here we assign our symbols. And again, after these rotations, this axis remains. So that axis is our E. And right now, after this rotation, the K axis moving to Z. So that is where we're going to assign our coordinates Z here. Okay. So under these situations, basically you can see right now the S and Z are taken into the original. This is again from here. This is the beginning of the first operations. And right now we're going to have the first operations. And so in the first operations in our axis, so here this is the end of first operation. Right now we're going to do this one. So this is one axis, one y-axis, k-axis. So one x, one y, and k-axis. So right now we're going to rotate is 90 degrees minus L. Okay, so doing this way. So here the k will move to here, and I-axis will move to here. This one will be aligned to our z axis. This one will be aligned to our s axis. Okay. So under this situation here, this is the angle 90 minus L. This is 90 minus L. So from here we can write it up. So here the two vectors are expressed in this plane, in the plane spanned by k and one axis. Okay, so here, so from here we can project okay, this amount is cosine and 90 degrees minus L, and that is in positive one direction. So this is the cosine 90 degrees minus L in positive x directions, and this amount is sine of this angle, and in negative k, so that is minus sine 90 degrees minus L. Okay? And for the y-axis aligned to our e-axis, okay, so that is 0, 1, 0, because e-axis equal to one axis, and that is the reading. And for this one, we project into the two components. Again, this is component has a magnitude cosine 90 degrees minus L, and that is in positive k direction. So z-axis decomposed into two components. The first component is cosine L in k directions, cosine 90 degrees minus L in k directions. Okay, and the second component has a magnitude sine of this angle in one direction, so that is sine 90 degrees minus L in the one direction. So that is what we read here. So here we define this as a matrix defined as the R2. So following our previous the formula as easy, that is a coordinate in the new coordinate systems, basically equal to R2 multiplied with this coordinate system. This coordinate system in turn is R1 multiplied with that one. Okay, so basically this is in IJK, and this is the coordinate in SEZ. So that we build up the transformation of the coordinates. And if you like, you can implement the calculations here. Okay, if you like, you can implement this one. R2 basically equal to this one becomes sine, right? So sine L. And 0, and sine 90 theta minus L basically become cosine. And 0, 1, 0, and this is cosine L, and 0, and that becomes sine L. So this is R2, and R1 we simply copy from there, cosine theta, sine theta 0, and minus sine theta cosine theta, 0, 0, 0, 1. Okay? So if you implement the whole thing, that will be the big function. You don't need to memorize. This function will be on the cheat sheet, or at least it will be on our textbook. And that in our textbook and defined as a D matrix. Okay, so that is a D matrix in the sections 2.6.11, and that is in our textbook. So you can refer to there. And the reason why I spend, at least right now, you can see more than 2 lecture hours talking about this kind of transformation, because this is the part that most of the time students feel confused. They simply don't know why the matrix coming out from here, and that kind of gives them the mental barrier to move on for picking up this matrix for doing something. So that is the major reason. And why, again, why we pick up this kind of notation, please review to the lecture notes about 2 lecture hours before. And that one, starting from the introduction of the review of the transformation of the coordinate system. So starting from there, the whole thing is kind of this systematic. Okay, so that is the one we have this. And we're going to use this D matrix to do something. And in particular, you can see SEZ is the local coordinate systems. And at a different radar size, they have their local different SEZ. So basically, SEZ, we call the topcentric coordinate systems. That can be used for getting the reading of the data from radars and convert it into the IJK coordinate systems. Okay. So on campus, we have at least 4 radar sites. 1, 2 on the west ridge into the forest, and 2 in the building, on the top of the buildings. So basically, per each radar site, they have their own local SEZ coordinate systems. Okay, so from here, we should be able to calculate the information. So that is about the SEZ.